So we have Holy Cross core component mock, and this is mock number 4, and we are up to question 5. Complete the diagram to show the reaction between two molecules of glucose and the products formed. Right, does this look like glucose? Yes, it does look like glucose. They haven't shown the rest, they've only shown the interesting bits of the molecule. So a general tip with drawing these in exams is to keep the style of what you've been given, but just amend it using your own knowledge. So here we're going to still have our main bit of molecule, so we're going to keep that exactly the same, and on this one we're going to do the same. But what's going to happen is we're going to lose water from this. Lose water from this one there, so H2O. You can't do that. It's better if you do it this way. So in this area here, we're going to get rid of H2O. So that's going to disappear, and it's going to leave us with this O connected between these carbons, and the hydrogens are going to stay the same. So the most common mistake here is to do something with these hydrogens. So I'm just going to leave those where they are, and we're going to show you this nice glycosidic bond there. So, but where did this go? It must be there somewhere. Well, I'm going to write plus H2O, and now that is completely balanced. So we kept the style. We haven't made anything up. If you start putting the rest of the molecule on, then you leave yourself open to making mistakes, and then if you do make a mistake, then technically it's wrong, and they might not give you them out. Name the organic molecule formed. So this is a disaccharide, but you know what a disaccharide between two molecules of glucose is, and it wants the name rather than the type, so this is maltose. Name the inorganic molecule released. Well, there it is, H2O. Inorganic, meaning it doesn't have a carbon chain in it, so that is water. And the type of reaction, well, you should know by now, building things together in biology uses condensation reactions. So reasonably straightforward so far. There's lots of examples of you having to do that sort of thing in the past questions, so you should be used to doing that. Over the page. One species of bacterium, Streptococcus mutans, produces the enzyme glucosyl transferase, which catalyzes the polymerization of glucose molecules. Wow. And polymers of glucose form part of the plaque on teeth and leading to dental disease. So it's told us quite a lot of information there, which might be quite useful later on. Where's our enzyme? There's our enzyme. So the enzyme, helpfully it's got an A's on it. It tells us it's an enzyme as well. Where's our substrate? And there we are, that's glucose. That's our substrate. So in any sort of enzyme question, it's always good to identify the substrate, the enzyme, and the products. And the products, polymers of glucose, there we are, so that's our product. What is polymerization? Well, that is, we started here building a glucose chain, so we just got 2 there, but if we keep adding them and make a chain of glucoses, then that's a polymer. So these are monomer units, mono 1, and polymer means poly, many. So making a chain. So polymerization is joining together monomers to make a larger molecule. So joining monomers together to make a larger molecule. Two scientists developali I have to ask Mrs. Knight how to say that properly, and Musa carried out experiments. One's got a rubbish name, one's got quite a nice name there. They used this enzyme and found out that its activity was affected by iron sulfate. Okay, and what have we got in this table? We've got the activity in some unspeakably horrible units, and it starts off lots of activity and goes down as iron sulfate goes up. So already you're sort of going, right, this is some sort of inhibitor, because when we add it, the activity of the enzyme goes down. So iron sulfate, that's our inhibitor. Plot the data on the suitable graph on the grid. Right. Okay. This grid is a little micro grid. So we are wanting to draw this mini graph. Which is our independent variable? Which is our dependent variable? Independent variable. Well, that's the thing that I am changing. I for independent. And look at this. 1, 2, 3, 4, 5, 6. That's the thing that we are specifying. So that's our independent variable. And our dependent variable depends on the experiment. So we don't actually know it until we've done the experiment. And that's these numbers here. So that's our dependent variable there. So our independent variable is going along the bottom. You idiot. And our dependent variable is going up the side on the y. What are these? Well, we've got, I'm just going to copy these out so I don't get it wrong. Iron 2 sulfate. This is 2001. Since they've done that, they've decided to put an F in there instead of pH, which will annoy the Brexiteers. Concentration. And the units there, millimolar. So if I copy that out exactly, I can't be criticised. And again, this horrible set of words here we go, glucosyl transferase activity, and the units are labelled product micromoles, whatever that is. Okay, you don't know what that is, I don't know what that is. Some Mr. Musa or Mrs. Musa might know what that is. So we're going to draw this. We need to choose a scale now. So we've got to go up to 6. So how many squares have we got? So 1, 2, 3, 4, 5, 6. So probably about 5. We're trying to go in regular intervals. So I'm going to go in 5s here. So we go 5. That's 1, 2, 3, 4, 5, 6. That's going to fit on nicely, is that? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. On 2 of the other mocks you've got graphs to do as well. So this is quite a common skill. This is actually looks a bit like the easiest graph that we've had to draw. So yeah, lucky beggars. And 0.0, 1.0, 2.0, 3.0, 4.0, 5.0, 6.0. So that's used more than half of our graph paper going that way. And going up here, what's our highest number on our X? We got 60. Well, we went up to 6 before. So it's going to be roughly the same sort of scale. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Why they can't put bold lines on this, I don't know. Maybe they did and it didn't photocopy. 1, 2, 3, 4, 5. Or maybe they're just heartless people that enjoy watching students suffer. That's probably more like it. So we have got 0 again, so we can keep our 0 down there at the origin, so 0. And this goes up in tens, doesn't it? So 10, 20, 30, 40, 50, 60. So there's our scales. And we've got nice regular scales. We're not just going to stick these numbers randomly on the side. We've got a proper scale that goes up in a sensible kind of linear way. No big jumps between numbers. All exactly what you want to see. Now we just need to plot our points. It's a lot of work this for 3 marks, isn't it? So let's start off with 0, iron, 60. There we are. Right, in some other examples, I've had to eat my words, but draw this in pencil and then you can rub it out when you make a mistake. Draw it in pencil. Draw the axes in pencil, the points in pencil, draw the labels in pencil, everything in pencil. I'm going to do this in pen so it sticks out well on the video, and I'll try not to make a mistake. It doesn't always happen. So 1.0, 25.2. So there's 20, 25. Where the hell 25.2 is a mystery, but just above 25. 2 is 12. So each square is worth 2. So that will be there. In an exam, they quite often will give you a squares tolerance on this, but you can be exact. 3 is 5.2, so we're looking at 5 halfway between 0 and 10. 4 is 2.4. 5 is 1.6. Yes, why did they give us a postage stamp to draw this graph on? 6 is 1.2. So there somewhere. I'm going to be a biologist and drawing these up dot to dot with a ruler, because my biology teacher told me that if I did that, I would always get the marks for drawing the line of best fit if they didn't tell me to do any other method. So I'm going to do that, and it's nice and easy. And I think you'll admit that looks absolutely fantastic. So the marks for a graph are correct. I'm just looking at the mark scheme. Correct axes, iron sulfate concentration on the bottom, the enzyme activity at the side. We've got units, a suitable scale using at least half the available space. Plots are visible, clear line, no extrapolation. Oh, fantastic. Use the graph. So this is where you've hoped you're drawing a decent graph. Use the graph to calculate the concentration of iron sulfate that would decrease the activity by 50%. So our maximum activity is 60, so 50% of that would be 30. So now we need I'm going to use a different colour just to make this stand out, but you would be still using your pencil. So 30 is half of 60. So 30 is half of 60. There we go. And then that is going to go down from there. So you could just read this off, but I like to draw them on. And then what have we got here? So each square is 0.2, so 0.2, 0.4, 0.6, 0.81, and that is going to be 0.9, our answer there. So our answer there is the concentration, so that is 0.9. We need units here, millimolar. Calculate the percentage. You were just waiting for that, weren't you? Calculate the percentage by which a 3 millimolar iron sulfate solution would decrease the activity of the enzyme. Not every student got this right, but with a bit of practice you'll be able to do these. Show your workings. Well, actually, you could almost guess this from the table. So if it went down to 3 on this scale here, well, it's gone from 60 to 5. So you could say, well, it's quite a lot. If it went down to 0, that'd be 100% difference. We've already done 50% difference, and it went down to 0.9. So our here was about 50%. 0 would be 100%. So what's going to be 5? So it's going to be a fairly low number. And we can do this with a nice equation. Our equation is the percentage change, we'll do percentage decrease equals the decrease divided by the start times by 100. So what's the... Now, by the way, if you use this every time, you'll get the right answer. Okay? So use this every time, you'll get exactly the right answer. What's our decrease? Well, our decrease has gone, so 3, so we're going down to this level here. So from there to that, what's the decrease? So our value of activity at the start is 60. What's it gone down to? 5.2. So that's our decrease there. What's our start value? And this is the most common error, is not using the right start value. Well, it's decreased from its original value, so that's our start value, 60.0. Okay, and then all we need to then that we still by times by 100. So let's fire in some numbers here. So 60 minus 5.2 is 54.8. So that's 54.8 divided by 60.0 times by 100. So 50.8 divided by 60 times by 100, and that's our answer there. So 91.333. I'm not going to write as my answer 91.3 recurring. Okay, so I'm going to use the guidance that I've been given to choose a sensible level of precision here. As they've given us 1 decimal place all the way through this, then I'm going to give it to 1 decimal place as a most sensible option. So 91.3% decrease. And that's your answer. So just using this equation here, percentage change, so either percentage increase or decrease, and always remembering to use the start or initial value on the bottom, you'll get the right answer. Okay, and then we are going to move this across so we can get some more light. I'd put another light bulb in my house, but it's too expensive. These two scientists discovered that iron sulfate acts as a competitive inhibitor. Describe the mechanism for competitive inhibitors. Right, okay, we're on home territory. So even if I screwed up all my graphs and maths, I'm going to get these marks, these 3 easy marks for describing how competitive inhibitors work. Okay, so imagine the enzyme there, the substrate might look like that. So that's our substrate, this is our enzyme, and that would fit in there and be complementary. But our inhibitor might look something like that. But it would also be able to fit in, and if it's in there, then our substrate can't get in. And that's basically the story we're telling. So the inhibitor competitive inhibitor competes with the substrate for the active site. The inhibitor fits into the active site, so inhibitor fits into the active site, and this blocks the active site for the substrate. There's only 3 marks here, so we've hit those 3 marks. We could continue, no enzyme substrate complex can be formed if we've got this blocking in place. And what else can we do? Well, we forgot to mention this is a similar shape. So inhibitor is a similar shape to the substrate. So similar, we can't say same because that's not the same shape. Okay, so it's a similar shape, then they won't let you have that same shape. But what is the same is the complementary fit. So the inhibitor has a complementary shape to the active site. I'm just trying to get that the right around. It's complementary to the active site. It's not complementary to the substrate. It's similar to the substrate and complementary to the active site. It's complementary as a kind of fit, like a hand fitting in a glove. The complementary shape. And we could mention here, it doesn't really ask for that, but we could mention the concentration of the substrate would affect the amount of inhibition. But it doesn't specifically ask for that. It's on the mark scheme, but I'm not going to add that. Suggest a possible use for the discoveries. Way back in the distant past, right back in the beginning, so you go, right, hang on, why did it tell us all of this stuff? So polymers of glucose form part of the plaque on teeth. Well, if we inhibit this polymerization, then that would presumably be better for teeth, because plaques on teeth, that's you can scrape off with your finger, your dentist doesn't like. So that's our possible use. So add our inhibitor, which was iron sulfate to toothpaste, mouthwash, drinks, anything like that, to prevent plaque formation. So sometimes these do say suggest, like you could use your chance to come up with something absolutely brilliant, but we don't really want that. What we want is something based on the biological knowledge, or something that is to do with the biology that's told you in the question. So no chance to be an original genius here, I'm afraid. So nice logging in some questions for 17 marks.